Hello, an electronic code lock is a security device that grants access using a numerical sequence, a PIN code, rather than a traditional physical key. These systems are common in offices, apartment complexes, and increasingly modern smart homes. In some of my previous videos, I described several different ways to make a simple electronic code lock. This time I will show you how I developed and built a prototype for a real code lock, which in its characteristics is much more advanced than many commercial devices of this kind. The test prototype contains a real mechanical code lock with standard dimensions. During the development, I gradually solved the problems one by one. I decided to use standard components that are easily available on the market and are relatively inexpensive. Here is what the prototype looks like, made on a plastic board for greater visibility, and easy modification is necessary if necessary during development. I'll start with the electronic components. The heart of the lock is an ESP32 microcontroller board, specifically placed on a suitable socket, adapted for easy modification without soldering. Then a battery pack of two series connected lithium-ion batteries that provide a voltage of 7 to 8 volts. At the moment, I didn't have a charger for such batteries, so I used this constant current, constant voltage stabilizer. I set the output voltage to the 8.4 volts and the constant current to 0.6 amperes. In this way, the board successfully performs the task of a charger. Then we have two resistors in voltage divider connection that bring the appropriate voltage level to the D2 of the D2 pin of the microcontroller unit. In this way, the battery capacity is measured. This small board is an ACS712 current sensor and serves to protect the motor. The sensor measures the current through the motor, and if it exceeds a predefined maximum value, this happens, for example, if the lock gets stuck and stays in one place, then the MCU turns off the voltage supply to the motor. This is a 5-volt regulator that provides power to the current sensor and the Hall effect sensor. On this small cooler has a MOSFET with two resistors, and its purpose is to turn off all circuits when the lock is idle. This way the huge battery saving are achieved, which is crucial in this type of device. Next comes a very important part, which is a combination of Hall effect sensor and permanent magnet, which determines the initial home position of the key. This is home position. This combination greatly simplifies and secures the way the MCU controls the lock. And finally, the motor that moves the key in the lock. In this prototype, I use a small cheap servo, modified in a way that it can move continuously in any direction. We will not dwell on the method of modification here, because it is explained in detail in many videos, and the procedure is relatively easy. I choose this particular way to moving the lock because of its universality. If in the final product we use a larger servo with metal gears, then there is no need for any change to the code. But also, with minimal changes, a brushless motor with a bidirectional driver or a regular motor with a H-bridge driver can be used also. Then I made a special bearing for the lock so that the motor can move the key left and right. So we have approximately realistic conditions during testing. Although all these electronics using SMD components can be placed on a PCB slightly larger than a MCU device development board. Now let's move on the software part. The code is made in a way that almost every phase of the lock's operation can be changed at the very beginning without having to walk through the entire code. This is a crucial equipment in this type of development project because very often when testing and changing components, quick changes need to be made in this code. I will describe all the variables that can be changed directly as well as their functions in the circuit. At the beginning, all 5 pins of ESP32 used in this project are defined here. Then comes the interval at which data about the battery status is sent. In my case, every 10 seconds. Offset is the value at which the server stops when no movement command is sent. This value depends on the accuracy of the 2 resistors that are built into the modified servo. With SU and SL commands, the speed of movement of the servo during unlocking and locking is defined. Ignore time is the time during which the Hall sensor is turned off when sending a command to the motor. Specifically, if this variable is 0, the motor will never start. Soft start time is the time after which the motor will start moving. This allows current peaks during motor startup to not be measured, which could give a false alarm for a stalled motor. Brake pulse, defined in microseconds, is used for fine-tuning so that the magnet should stop exactly under the home Hall sensor. This brake value is determined purely experimentally and depends on the motor used. Next, current limit is the current value in milliamps above which the motor is signaled to be stalled and a command to shut it down is sent. To avoid false alarms for a stalled motor, it is stopped only if there is a certain number of consecutive measurements above the previously set current limit. This number of consecutive measurements is defined by stall samples. And finally, float 0 is used for calibration to display the correct battery voltage value. For access control and password entry, I use a smartphone with an Android application, which by the way is my first Android application. It probably could have been done much more professionally, but that wasn't my primary goal in this case, but rather a way to have full control over the lock. When activating the application, a field for entering a pin appears, which is the simplest possible protection. I mentioned earlier that this is my first Android application and I did not intend to waste a lot of time on its implementation. Always the security part is extremely important in this project, so multiple priorities and levels of protection should be implemented in the final product. By entering the correct pin, we enter the main menu. In my case, correct pin in 1, 2, 3, 4. First, the application connects to the lock via Bluetooth Low Energy connection. Here the status of the lock locked or unlocked is displayed, and below it a state of the battery, which is an integral part of the lock. The state of the battery is accompanied by corresponding different colors. In the middle of the screen there is a large round button with which we unlock or lock the door. This is the basic user menu and should be enough in 99% of case when using the code lock. However, sometimes it can happen that the lock gets stuck, or we want to change the number of turns when locking or unlocking. For this purpose, there is another settings button that enters the next menu. There we have the opportunity to first change the number of turns of the key, 1 default or 2 as desired. This setup becomes active after exiting the setting screen. Then there are two more buttons marked with L and R that are used for manual movement of the motor. This option is very useful in case the key gets stuck, because manual movement is defined in the code in such a way that the servo turns with the greatest force and the current sensor is bypassed. Next comes the most interesting part, and that is how this device behaves in approximately real conditions. I say approximately because what is missing here is the locking-unlocking mechanism that is mounted inside the door. However, today's locks are very precisely made so that only a little more force is needed to move that mechanism. Also, let's not forget that the final product would use a servo that is many times stronger and of higher quality than this $1 small servo. The door is currently closed, and if you want to open it, we press the button. Door is open, and now door is closed. Open, closed. Now in the settings menu we can change the opening closing method to 2 turns. Settings, 2 turns, settings again. The lock works the same, but now with 2 turns. If the lock gets stuck in a neutral position, we can try to unlock it by manually turning the motor, which is now moving with maximum force. So manually left or manually right. Now I will connect an ammeter to see the total consumption of the device when it is idle. This is actually, besides functionality, the primary goal to achieve as little consumption as possible when the device is not in use. The duration of batteries on a single charge depends on this. Let's start the device. It can be seen that the idle consumption is about 30 milliamps, seeming little, but in fact this is a huge value for this type of device. And of course, while functioning, the consumption is greater. Now if I disconnect the application, again the consumption is about 33 milliamps. The code includes light sleep mode, a compromise between deep sleep mode and normally active microcontroller unit. The difference between light sleep and deep sleep is a few milliamps, but in light sleep mode connecting to the Bluetooth light energy is almost instant, unlike deep sleep where it can take tens of seconds or more, which would not be practical at all. Currently the largest energy consumer is this little regulator located on the MCU board, and which reduce the input voltage from 8 volts to 3.3 volts required for normal operation of ESP32. If I replace this linear regulator with a switching mode regulator, unfortunately I don't have one at hand at the moment, the total consumption will be reduced to 3 to 5 milliamps, which is the absolute minimum for the device to function normally with this hardware. So with all the hardware and software modification to save power, the average battery would last a maximum of about a week with normal use of the lock. However, it is known that such locks from well-known brand manufacturers can work for 3 to 6 months on a single battery charge. The secret is in the use of highly specialized chips designed specifically for such battery-powered devices. One of the manufacturers of such chips intended for industrial use is Nordic Semiconductors, whose specialized chips have several thousand times lower power consumption than, for example, ESP32 in deep sleep mode. These chips practically do not consume any power when in standby mode. However, these industrial chips use a special framework developed by the manufacturer, and the way they are programmed is characteristic and different for each series. And finally, a short conclusion. With this project you could roughly see how complex and time-consuming the development of device is before it reaches commercial production. In particular, this code lock, despite all the measures taken, especially for energy saving, does not meet the standards for a battery-powered device of this type, but it is certainly an excellent basis for further development with specialized chips, taking into account that the programming logic remains exactly the same.